Hi, have you ever seen one of these images, or one of these machines? These are ultrasound images, taken from ultrasound imaging machines that are used thousands of times a day across the world. They can be used to look inside the body without any incisions or harm. Many lives have been saved because of the devices, but they wouldn't exist if not for some important physics. The Doppler effect, a physics concept concerning the observation of a change in wave frequency from a moving object, is utilized in medical ultrasound imaging. It enables doctors to non-invasively diagnose certain problems anywhere in the body, especially with the heart or a fetus. The Doppler effect was first proposed by Christian Doppler, an Austrian physicist, in 1842. Because it is a physics principle concerning waves of all kinds, it can be applied to many other fields, such as biomechanics and astronomy, and in devices like radars and satellites. To understand the Doppler effect, we first need to understand sound. Sound waves are mechanical waves that are produced by rapid variations in pressure. Sound can travel through many mediums, such as air and water, but not through a vacuum because there would be no mass to pressurize and depressurize. Hence the phrase, "no one can hear you scream in space." Like all waves, sound has peaks and troughs. The peaks, also called crests, representing high pressure, and the troughs representing low pressure. A wave cycle of a wave is any section during which it goes from one peak to the next. Frequency is the number of wave cycles that occur every second, the unit being hertz. The distance between consecutive corresponding peaks or troughs of a wave is called wavelength. The smaller the wavelength, the higher the frequency. Humans can only hear sounds up to about 20,000 Hz, but ultrasound, defined as any wave above 20,000 Hz, is usually 2 to 20 MHz in medical imaging. A good way to visualize the Doppler effect is with an analogy. Let's say that you and your friend are standing outside. Your friend has a bucket of tennis balls, and will throw one directly to you every second. Each ball represents the crest of a wave. Your friend is the object emitting the ultrasound, and you are the receiver. If you and your friend are stationary relative to each other, he will throw the one ball at you every second, and you will receive one ball every second. The wavelength will be constant. The Doppler effect happens when he is moving towards you or away from you. If he is running toward you, still throwing one ball a second, you will be receiving more than one ball a second, your reception of the balls being at a faster rate, because the time it takes for a ball to reach you will continuously decrease. The wavelength will decrease. Similarly, if he is moving away from you, you will receive less than one ball per second, your reception of the balls being at a slower rate, because the time it takes for the balls to reach you will increase each time. The wavelength will be larger, and the frequency smaller. This is the Doppler effect, the apparent observed change in wavelength, and consequently frequency that occurs due to relative motion of the wave-emitting source. By detecting how often the tennis balls, or waves, take to reach the receiver, the Doppler effect can be used to detect whether objects are moving away or towards the receiver. This is the basic equation of the Doppler effect. Although the equation differs depending on the physical situation, we will focus on the main one, which assumes that the receiver of the waves is stationary. It solves for the changed frequency the receiver of the waves or tennis balls detects. Fi represents the initially emitted frequency, and Fo represents the observed frequency. Vr represents the velocity of the receiver, and Vs represents the velocity of the source. C represents the speed of sound through the medium, which is body tissue. Doctors know C and Fi beforehand, and can observe Fo. The goal is to find Vs. The initial frequency of the wave is reduced by C plus C over Vs, which is the ratio which shows how the source is moving toward the receiver. This yields the observed frequency, which is what the receiver detects. If the source is moving away from the receiver, Vs is negative instead of positive. Ultrasound machines create ultrasound waves by using special transducers called piezoelectric crystals. These waves bounce back to the receiver off of structures in the body, and their strength and timing when received enable a computer processor to create the image the doctors see. Now we can connect the Doppler effect to ultrasound imaging. There are many different types of ultrasound imaging in medical practice, but for the explanation, we will only focus on a few. A-mode ultrasound is the simplest, but least commonly used. A single stream of waves are fired, and the amount of time it takes for them to come back determines the depth of a barrier beneath the skin. B-mode, also called 2D mode, is more commonly used and involves an array of piezoelectric crystals repeating the linear A-mode scan to create a 2D image of the structures beneath the skin. N-mode is just frequently repeated 2D mode scans, creating a live video. The way the Doppler effect connects to this is by measuring not only the time the waves take to come back, but also the shift in frequency as they come back. If you remember the analogy, the closer the wave emitting point gets, the shorter the wavelength and the frequency become, and vice versa if the point is going away. In the body, the objects the Doppler information is most commonly used for are groups of blood cells as they pass through arteries. When the blood cells move towards the machine through the arteries, they slightly compress the wave and wavelength when the waves bounce back, causing blue shift. When the blood cells move away from the machine through the veins, they slightly dilate the wavelength on their way back, causing redshift. Zing redshift. These are shifts that the machine can detect. This enables the machine to distinguish a nerve which does not pulsate from a blood vessel, and distinguish an artery from a vein, depending on which way the blood is flowing. This concept is very similar to the famous sonar bats use to detect their surroundings without eyes. On the screen of the machine, the Doppler information is displayed on top of the 2D image gathered with timing and red indicating an artery where the blood is moving toward the machine and purple indicating a vein. The tennis ball analogy also showed us that depending on the size of the change, the velocity of the source can be determined. The same principle can be applied to the blood, so that the velocity of the pulse in specific areas can be found, determining how clogged an artery is. Being able to calculate blood velocity and direction and numerous subdermal irregularities non-invasively with the Doppler effect in ultrasound imaging is invaluable to medical professionals. It can help diagnose problems with obstetrics, cardiology, and muscle motion. It's also useful because it doesn't harm the body, it is inexpensive to use, and it can be portable and flexible. It is a wonderful example of the crossing of biology and physics, which is of growing importance in today's world. Thanks for watching. Bye.